go ahead and unmute myself. Let me get everything set up. I got MVP, that's what I'm talking about. All right, we can shut all this down. Let's go here to the waiting room. Let me go here. Close all these tabs. Thank you. Here, agree, come on, this is time for class, courses, this one, time this one. Testing, that looks good, that looks decent. Let's actually hop back over here. Testing.
Yeah, we hear
you. Oh, it is time. Okay. So let's do it this way actually. Let me check one other thing. I think we are good to go. All right. So greetings, YouTube. Beautiful Mind here, aka Professor Pfeiffer. Let me see if there are any announcements. So I did start streaming a little bit early today. Oh, I'm looking out the window now. The moon. I mean, the moon always looks surreal to me. You know, we only see one side of the moon. Like, you ever heard of that phrase, the dark side of the moon? it's really creepy when you start studying it. It's like it's not a spinning rock. Somehow we only see one side. Doggone it. I think this is the student. Okay. Who else is in there?
Professor, I have a quick question.
Let me finish the announcements. Like, write it down. Just give me like a few minutes, because it might get answered. Let me kind of go through my announcements, and then we'll go from there. Then I'll be ready for that. Only real announcements. Exam 1 is available now. It's due this Sunday at midnight, going into Monday. You get unlimited attempts at all assignments. It is set to take your highest score. You can actually submit all assignments past the due date. There's a final deadline, like closer towards the end of the semester. But even when we submit our assignments late, there's a 10% late penalty. So if you really wanted like an A- on any assignment, you can still get it. It would just have to be a perfect score. Attendance does not get factored into your grade. I use attendance just for records. Attendance really only becomes an issue if we accumulate like 4 or more unexcused absences. And I know we kind of been getting used to our rhythm and getting into the swing of things. So don't stress too much about the previous weeks. But going forward, the main thing is we're doing an asynchronous schedule. So, main thing is you just need to check in each class, get your attendance credit. If you don't have any questions, you're free to keep going. But I'm just going to take this time to answer questions or go through the homework. If there aren't questions, I'm going to just make my way through the homework. Let me see if there's anything else that I need to say. Also, if anybody needs information on the tutors, let me know. I can put it in the chat, or I'd rather do an announcement, like I'll forward the email to you all. I know we have at least one tutor. It would be via Zoom, but he's good. Like he's good. Like he seems to have a good rapport with the students, and he's knowledgeable. So if anybody needs to connect with the tutor, I'll probably forward that anyway. Yeah, main thing is just get your attendance credit and get your assignment submitted on Pearson. Okay, I know there was at least one question, so I don't know if you wanted to go ahead and shoot your shot.
It was about something in your... Dang, where was it? The box link where you share files and notes, but I found where you do all the everything. So
yeah,
I look over.
Yeah. It took a while. Your class is up to date as far as that's concerned. So the question was about the box link. Your class is up to date, and so as I complete assignments, now I don't know if I think I did it on Monday. I have it, but if it's missing anything, just let me know and I can get a copy there. But yeah, it's on our Blackboard page. Everything for us is on our Blackboard page, on that main page. Okay, attendance looks pretty good. We're missing a few people, so we'll track them down. I see a lot of names got added back, so that's good. We can kind of keep moving and doing what we need to do. Okay, so, and again, if you have questions, feel free to either unmute yourself or type in the chat. I do monitor the chat. Otherwise, I'm just going to kind of hop into the material. So let's hop over to Pearson. Did I lose my page? Oh, I probably took too long, and it probably closed it out. I got to reload it. Let me redo that. Let's go to the waiting room and let's get some music going while we wait. All right, so what I gotta do is gonna be here. So we're in week 4. Exam 1 covers, it's a lot. Chapter 1, Chapter 2, and 2 sections in R, like R4 and R5 or something like that. So we're gonna be working on the last part of Chapter 2 today. So let me just reload it. This question. Okay, that looks good. And so, like, I know I'm kind of talking over the music, but leading up to today, like as just an Easter egg, I went on the show, shared like my screen while I was gaming. It was just a quick like brawl match. I need to change this one. other thing is right here. Let's just turn the volume back down. Okay. So show that, and we can hop back right here. Okay. Oh, so I got to redo my sharing windows. Man, it's like, it's so much that you have to do for like the stuff to behave properly. I feel like I need another processor, like a whole nother unit, just to, so it's not so much work on one device. We need that one, and we need this one. Share. All right, I think we're ready to rock and roll. So now, when I'm streaming, let me see. Am I streaming? Can I see my notifications? Oh, you're a pain. Come on. Okay, yeah, I am streaming. Okay. All right. So now, so let me see. We get out at 7:15, so we got about an hour. So we'll take about 30 minutes. Hey Siri, set a timer for 30 minutes.
Okay, 30 minutes and counting.
So we'll take 30 minutes and make our way through section 2.5. Now, also the way, because we're doing asynchronous, I usually do our lectures in advance. I try to make them in advance. And then, so what that means is that we can actually take class time to do it as a Q&A. So if you want to work over any questions, we can work over anything. Thank you. You know, we don't have to go the way we're doing it. If you like working through the homework or you want to talk about something, we can. So I just wanted to kind of remind you of that. Since our time is precious, I want to get to some questions from section 2.5, applications of exponential, I think it's derivatives, but let me try to get to some questions from 2.5. These so far are our review from previous sections and some things from college algebra. I want to try to get to 2.5. Okay, that was something. I guess we could start there. So these are just applications, right? So this one says a chemical substance has a decay rate of this per day. The rate of change of an amount n of the chemical after t days is given by this, okay? So this is the rate of change. Notice it's negative 0.082 times the original. Let n not represent the amount of the substance present at t equals 0. Find an exponential function that models the decay. So I think last time we said that something of this form, a function that's going to satisfy where this is the derivative is basically going to be the exponential function. So I'm going to take some notes. I know you can't see my screen right now, but I'm just going to, you're not going to be able to see my notes while I'm writing. Hopefully I don't have to reboot this as well. Let me move that out the way. All right, so this comes from, let's see, looks pretty good. This comes from week 4. This is day 8, 2.5 applications. Okay. Exponential derivatives. Exponential derivatives. Okay, blah, blah, blah. Like, and this stuff seems very like innocent and like, you know, like it doesn't matter. But I have like a former student. She's making her way towards law school, so she's like at state right now, and she has to like take. She's like, oh, y'all have to call back because I'm in class. They always call like I'll be busy. See, trying to mess up my stuff. But yeah, she was working on some stat stuff. I was like, yeah, I can look at it. And it was the exact same thing that we went through in my class. I was like, yeah, well, this is exactly the same thing. So I was kind of helping her with it. So I was like, okay, that made me feel kind of good. I always like to get updates from people and know that they're still doing well. But as long as you have my contact, if I can help you, I will. You know what I mean? Okay, so we have that the derivative with respect to t of some function n, or dn by dt, is going to be equal to negative 0.082n, right? It says that r has a decay rate. It tells us that the rate is 8.2% per day. Okay. So n naught represents the amount of substance at t0. Find the exponential function that models the decay. So I'm going to hop over to the tablet. And so we want to find some function that models this, right? So I think last time we said something to the effect of, let me write it the way I'm used to seeing it. So if we're going to do n, we would do some n of t will be some n naught e to the rt, right? So, you know, based on what we said before, when the derivative is something like this, a function that generally fits that is going to be the exponential model of this form. Is it going to show? Not showing. It shows that, but it's not showing this other thing. Let me try this again. Seriously. I don't think that's behaving right. Huh. I didn't know it did that. See if I choose a different color. Nothing. I didn't know it did that. Let me reboot this real quick. See if that changes something, because I'm doing some pen strokes over here and they're not showing, and I'm like, has it always been like that, or is it just like a glitch right now? And let me make sure it's showing here. Okay, let me see if it's behaving proper now. Okay, yeah, I don't know. It was just glitching. So now it's showing, because I was doing things like this and I realized that it wasn't showing on the screen. Okay, so I think we're back in business. So yeah, when we talked about this before, we said that a function that's going to satisfy this condition is going to be the exponential function, right? Okay, so they give us the rate. So we want to try to find, we want to try to solve for the initial amount. Let me think about it. Let me hop back to the question really quickly. A chemical substance has a decay rate of this. The decay rate of an object after t days is given by this. Let n not represent the amount when t is 0. Okay. Find the exponential function that models the decay. If t is 0, do we have something? Okay. So here we'll go with this, right? We'll go with the following. And then they gave us r, so yeah, we're just going to go with this. We're going to say that the function based on t, whatever the initial amount is going to be n naught times e to the rate. Now the 8.2%, we have to write that as a decimal, and if we're doing exponential decay, it needs to be negative 0.082, right? It just needs to be negative times t, okay? Where n naught is whatever we started with, right? So I think we need some more information to find the original amount. Let's try this result on Pearson and see what happens. So this is kind of like, this should be a review from what we did before, or a recap, okay? So let's hop over to Pearson. This is just the first one. So n of t. Before I submit my answer, I'm going to go to the question help and I'm going to click on the view an example. And I just want to see how did they put their answer for part A, right? That's all I want to see. I want to go continue. Okay, that's fine. Okay, I just want to see, yes, they kept their n naught, right? So yeah, this is exactly what we got. So we're going to submit what we have, okay? And so just see how, like, when I'm not sure, I just click on the view an example and it'll give me more details, right? That's what I would expect you all to do. N sub naught, let me try this. N sub 0, n naught, e to the negative 0.082 times t, okay? I'm gonna go with this. All right. So then after 5 days, blank will remain. Okay, so say the time, round to the nearest whole number. We need n naught. Okay, suppose that 700 grams of the substance is present initially, right? Okay, that's what we needed. How much will remain after 5 days? Okay, so let me take some notes here. So that was part A. Let's say part A started here. So then part B, so we had 700 grams when t was equal to 0. How much remains after 5 days? 5 days, okay, question mark. Hop over to the tablet, boom. Okay, I think we're looking good. So now we can solve for the initial amount, right? So when we started with 700 grams. So that means our model is gonna change to n of t is gonna be 700 times e to the negative 0.082 t, right? Because the n naught is how much we started with. So then now only thing, we just plug in 5 days and crunch the number. So then n of 5 is going to be 700 times e to the negative 0.082 times 5, right? So now it's time for me to break out my trusty dusty rusty calculator. Let me see. I'm gonna let that be. Matter of fact, let me go ahead and finish the attendance. So attendance was much better today. I think he's in the class. Let me check the attendance, the participants. Let me see. I thought I saw his name. Let me check again. Maybe not. Okay, I think it's just because it's such a generic name. Okay. I'm gonna just put absent. Let me go to my calculator. Okay. Reload and refresh. Every time I hear reload, I think of the Matrix, then I get really excited because they're about to come out with, they're about to release Matrix 4, and I'm just curious. Like, my curiosity is piqued to be such a popular, successful franchise. I'm just curious to see. My expectations are low for that movie, by the way. I have really low expectations. Like, I'm not expecting anything. Crosby. Yeah. If you're in my, let me make sure. I think I got. Let me make sure. But yeah, if you're in my roster, if you're in this call, I take attendance as I let you in. So yeah, you got your attendance credit. I know you're here. Yeah, but I get the sentiment. I get it. You want to make sure you get your credits. I get it. The main thing is get your stuff in Pearson submitted. That's the real thing. Like, make sure that stuff is in order. The rest of it will be fine. Okay. So we're just gonna crunch a number, right? So I'm just gonna do 700. Oh, not like that. Let's do it here. Dang, not even there. What am I doing? Okay, 700 times E. So I'm gonna hit second natural log to access E. Negative 0.082 times 5, right? Looks good. We hit enter. I think it said to the nearest gram. We got approximately 464. I'm just going to put 555 for right now. I'm going to go back and read the question around the way that they accessed around. Let me put my calculator away. Let's hop back over to Pearson. It says round to the nearest whole number. So if we have 464.5, the nearest whole number is going to be 465. So approximately 465 grams. Okay. So I'm going to say that's approximately 465 grams. Put that in the box. Okay, the style, gonna go like this. Okay, we're looking good. And let me copy. Okay, let's go into part C. So what's going to be the rate of change of the amount of the substance after 5 days? So the derivative says, basically the derivative is going to be the rate times your original function, right? That's what we started with. So all we got to do is basically take that answer and multiply it by the rate in decimal form, and we'll get the answer for this one. So I need to break out my trusty dusty rusty again. I'm just gonna crunch the number and go with that. I'm not gonna show this or write anything. I'm just gonna say times parentheses negative 0.082 close parentheses. The rate of change, the decay rate at that point is a negative, and it says to one decimal place, negative 38.1 grams per day. Negative 38.1 grams per day. Nearest decimal, one decimal place. Okay, I'm gonna go with this. On to the next one. Again, all I did there, if I want the rate at 5 days, I just took that previous answer times our decay rate, which was the negative 0.082. That's what it says. The rate times the original. Okay, so let me see. That was D. That was C. After how many days will half of the original 700 remain? So basically they're asking us to solve for T, right? We could use the half-life formula. I think half-life is, I'm not really sure, natural log of 2 over something, or H equals natural log of 2 over K, something like that. But instead of using the half-life formula, I'm just gonna use the exponential formula. It's the same thing. Half-life formula is much easier, but I'm just gonna do what I'm comfortable with. So let's hop back over to here. And we want the half-life. We want to see how long is it gonna take for half of it to remain. I'm gonna do the long way first, and then I'm gonna go back and look up the half-life formula and then just compare them, right? So if we got a function, if our function is n of t equals 700 e to the negative 0.082 times t, They're asking us to solve for t. If we want half, if we start with 700, then we want to finish with 350. So if we have 350 equals 700 e to the negative 0.082 times t, now we just solve for t. So if we divide both sides by 70, I think on the left-hand side we get a half equals e to the negative 0.082t. Then we take the natural log on both sides. Natural log on both sides. On the right-hand side, natural log and e are inverses of each other, so they cancel. On the left, you could leave it as the natural log of a half. Natural log of a half is the same as negative natural log of 2, because if you do exponential properties, this is going to be basically the natural log of 1 minus the natural log of 2, but natural log of 1 is 0, so you get this. On the right, we have negative 0.082t. So then ultimately, the half-life, which is our t, is going to be the natural log of 2 over 0.082. All right, so the half-life formula is natural log of 2 over your rate, right? But notice, I think if we had just used, we would have gotten a negative result, but you know, if we had done it incorrectly. But anyway, I think this is it. We're just going to crunch that number. Let me crunch that number and submit it. So how long will it take? Whatever that number is. I'm going to go ahead and hop back over to Pearson. Let's see, we're going to go this way. I say a lot. I'm trying not to do it. It's like the more I try not to say the more I feel inclined to say It's really weird. And I'm like, well, I don't really care. I do, but I don't. Okay. Let's just being honest. I'm not here for clout or anything. I just like the platform. I like having a log of it. I use some of this stuff and it's just a digital log. Okay, so if I crunch this number, natural log of 2 divided by 0.082, I get, it says round to 1 decimal place. So it would be 8.5. So after 8.5 days. So 8.5. All right, so let me write that down. Let me see my time. Okay, we're looking pretty good on time. I'm gonna say this was approximately 8.5 days. Okay, I'm just gonna paste my box, shrink it down to size. Okay. All right, that was fun. I'll close this out. And let's go on to the next question. Okay, let me check so the chat looks good. We're gonna kind of let things be for right now. A substance decomposes at a rate proportional to the amount A present. Write an exponential equation that gives A left of an initial amount A naught after time t. Oh, okay. Choose the equation that gives this, where K is positive. Decomposes, it should be a negative exponent. If we're talking about exponential decay and K is positive, you got to have a negative up there if you're doing exponential decay. It looks like this last one, right? Because this one is missing the E, the exponential. I'm just going to go D there. Okay. There will be 1 pound left after how many hours? Okay, we got some stuff we can plug in? Okay. It's found that 10 pounds of A will reduce to 5 pounds in 4.3 hours. After how long will there be only 1 pound left? Okay, let's write this out. We can do this. So this is question numero 7. Número 7. Okay, so number 7. Habla español un poquito, pero es difícil para mí comprender las personas. Okay, anyway. So, this comes from section 2.5, question number 9. This is I guess a problem solving something, PS, whatever that stands for. We know we're working with A of t equals A naught e to the negative kt, okay? Now in part B, it says 10 pounds of A goes to 5 pounds in 4.3 hours. Okay. Hours. Okay. And then how long will it take when we have 1 pound left? Okay, question mark. We're gonna hop over to the tablet like this. Okay. So let me see. Now, from the information they gave us, it says if we start with 10 pounds and we finish with 5, that sounds like half-life, right? Okay, we just, and they gave us the time. Okay, so the half-life formula, the half-life is going to be natural log of 2 over r. Or we can also, this is synonymous, this is the same as r equals the natural log of 2 over h, right? Because we want to know the rate. So they gave us the half-life. So 10 reduces to 5, and that time is 4.3 hours. So that means that our rate is going to be, it should be the natural log of 2 divided by 4.3. I'm trying to think if I need a positive plus or minus in here at all. I'm going to go with this. So I'm just going to crunch this number. I had a really good lunch today. We went to Publix and they were like, oh, $5 sushi Wednesdays. I was like, up, no brainer. So I got me 2 pieces of sushi. It was really good. I feel good too. You know, you always gotta like monitor, make sure you're getting good sushi. So you don't want to play around with it, but it looked good. Natural log of 2 divided by 4.3, we get, I don't really want to round it. I'm going to write the approximation, but in use, I'm going to keep it exact until the very end. So this is going to be 0.1611. I'm going to say 97. It goes further, but I don't want to round until the very end. So I'm going to just let that kind of be for right now. Okay. So we have our rates. So then how long will it take for us to get down to 1 pound? Okay, so let's go back to our model. So again, our model that we're going to be using, we have this A of t equals A naught e to the negative kt. We have the k, so this is our k right here. I just keep using r, but we have our k. We want to solve for t, and the initial amount was 10 pounds, right? And we're going to finish with 1 pound. Yeah, so we can plug in, we know everything except for t. So we want to finish with 1 pound. We started with 10 pounds, and our rate, I'm going to use that exact version. I'm going to use the natural log of 2 over 4.3. I'm just keeping it exact. And the only thing we don't know is t. So if we solve for t, let's see, we can divide both sides by 10. We get 1 over 10 equals e to the natural log of 2 over 4.3 times t. Okay. If I take the natural log on both sides, so not ln of this guy and ln of this, on the right, the natural log and the e cancel. On the left, that's going to be negative natural log of 10. Okay, natural log of 1 over 10, it's the same argument, is the same as natural log of 1 minus the natural log of 10. So the natural log of 1 is 0, so that's where that comes from. On the right-hand side, we're going to be left with the natural log of 2 over 4.3 times t. So then multiply both sides by the reciprocal. Ultimately, t is going to be equal to, let me think about it. Oh, you know what? Our model, we have a negative right here. So that negative is here. So that negative is here. So then we get our double negatives and they cancel. Because I was like, we should have had a negative that should have canceled. So I forgot to include it from the model. So now if we multiply both sides by the reciprocal, t is going to be equal to 4.3 times the natural log of 10, all divided by the natural log of 2. That's the exact answer. You don't have to do it this way. I'm just comfortable doing this way. If you wanted to take that decimal, just write out the long decimal all the way into the end and then round at the very end, right? So I'm going to put that in my calculator to get that result. Let me at least go ahead and open up my calculator. If I can get this to behave, come on. Okay, and I'm actually gonna go ahead and hop back over to Pearson. Okay, so then it says do not round until the final answer, then round to the nearest whole number, right? So if I crunch this result, we got, on top, we got 4.3 times the natural log of 10, and I'm gonna say divided by the natural log of 2. Okay. And it says round to the nearest whole number. The nearest whole number is 14. What is this? The time, approximately 14 hours. 14 hours or minutes. What are the units there? 14 hours. Paste. Okay, let's submit. Let me copy this. Let's submit our result. We got 14, cross our fingers, and we're gonna submit. God is good. All the time. We got 5 minutes before my alarm goes off. Hey Siri, stop the timer.
I stopped the timer.
I want to do at least one more from here. If I want to do something a little bit different. Half-life T is this. Find a decay rate. Oh, okay. This should be quick. So we said half-life was the natural log of 2 divided by R. Similarly, we could say R equals the natural log of 2 divided by T. So if we want the rate, we would just say the natural log of 2 divided by 15. Let me do that. I'm going to do the natural log of 2 divided by 15. It says round to the nearest tenth. I get 4.6% per minute. 4.6, right? 4.6. So again, all I did, I said the natural log of 2 divided by 15, and it gave me 4 points. It gave me 0.046, but then you have to convert the decimal to the percentage. Let me try one more. The decay rate particular is this, where time is measured in years. Find the half-life. So half-life is just going to be the natural log of 2 divided by 0.028, right? So I'm just going to do natural log of 2 divided by 0.028. And that'll give me years, right? So the years, and it says round to one decimal place. So 24.8 years, approximately 24.8. So those were quick. I think that was good. I mean, I wanted to do more, but at least we kind of remember the whole half-life formula. Once you know the half-life formula and you're dealing with half-lives, it's fast. It's much more simple, right? It's fast and simple and efficient. The epitome of mathematics. Because math is all about simplification, right? You know, like KISS, keep it simple, silly. You know, one of the concepts I saw in a poster when I was a student at Morehouse, it was like, there is no such thing as complex. Things that we consider to be complex. Complex is just a long string of simple ideas, right? So the reason we struggle with complex ideas because we haven't taken the time to go through the basics and make sure we really know the basics. Because when you really know the basics, you realize there's nothing other than the basics. Even when, like, it don't matter what it is. Like when I train martial arts, you see these people doing these long combos, but if you don't know the basics, then you can get overrun. But if you know the basics, again, the combos are just a long string of the basics, a long string of simple ideas. Okay, so I'm totally out of breath. I'm gonna hop back over. Let me hop to the waiting room. I'm gonna put on some music and switch. I gotta load the next section. make sure we're showing the proper thing here. Yep, that's what we want. That looks good. Okay. All right. So we're gonna go ahead. Let me check the chat. So I know it's kind of quiet. I know this stuff is kind of overwhelming. I'm kind of just going at my natural speed because these should be being recorded. They're streamed to my YouTube channel. You can always go back, slow it down, rewind, pause, stuff of that nature. So I just want to kind of like flow. But feel free to like interject if you have questions or we need to go back. Now is the best time to ask questions. It's a little bit harder because once we leave here, I'm like off and running. Time just moves so fast. So, you know, once I leave here, I'll be like busy a lot of times, but not too busy. You just got to get my attention. Okay. So this is section 2.6. Some more application. We're just going to be exploring some concepts behind derivatives of a to the power of x, exponential functions, and log functions base a. Right. So instead of e to the x and natural log of x, now we're going to be doing a generic base a to the power of x, and this is really like log base a. Right. So let me see, find an exponential function of this form that models the situation and then find the equivalent exponentials of this form. Let me see. It says the doubling time of 3 years and initial population of 550. Okay, so we start with 550. We're going to finish with, what is that, 1100? How does it look like that? What is the little t? Find the exponential function of this form that models the situation. What is the capital T? Initial population, we can plug that in there. Doubling time, what are these? Exponential functions, and find the equivalent exponential model of this form. I'm going to go to view an example real quick. Little t and capital T, is that like doubling time? Let's see, if a quantity increases n-fold over a fixed period of time, is given by this. I just need an explanation. Okay, if a quantity increases n-fold over a fixed period of time t, then the quantity p of t at time t is given by this, right? So t is, let me see, let me try the next one. Let me go like this. That's a little bit better. Continue. Okay, yeah, so we will plug that in. So the doubling time, so n equals 2. Okay, let's keep going. So then the fixed time is 6. Where is that coming from? Oh, doubling time is 6. Okay, so n is 2. So then the capital T is 6, all right? N is 2, capital T is 6 in that case. Okay, so if we have capital T, we have the initial amount. Oh, that's n to the power of. Okay, I was missing that. So n is 2. They give us n, they give us capital T, they give us the initial amount. The only thing we don't know is t. So yeah, we have all that stuff. I think we can take it from there. Okay, so I'm not gonna look at the help. I'm gonna kind of just jump into it. So this comes from, let me get rid of this. This is what, week 4. So this is week 4. This is day 8. This is 2.6 derivatives of a to the power of x. Because before we were doing e to the power of x, and I'm pretty sure it's log base a. It's like a generic base, log base a of x, right? That's what we're working on here. So this is question number 6, and this comes from section 2.6, question number 1, right? So we're asked to find a function of the form. We have p of t equals p naught times n to the power of little t over big T, okay? And then find an equivalent model of the form p of t equals P naught times e to the RT. Okay, we're going to try to make our way through this. It says we're also given the doubling time, 3 years, and the initial population. Let's move that on the next line. March. Yeah, I'm not doing that right now. Initial population was 550. Okay. I think those are all the notes we need. All right, so let's take it step by step. So we found out what all those components, so let's go back to the model that was given. We were given this P of t equals P naught times n to the power of little t over big T. We're also given the doubling time, so that means our n is 2. The doubling time was 3 years, so our capital T was 3, and our P naught is 550, right? So they gave us all this information. Only thing we don't know, what are they asking us to find? Let me go back to the question. Find an exponential model of this form that models the situation. Okay, there's nothing to calculate there. We can actually just put all that stuff in. Let me see. So I'm just gonna, let me hop back over to Pearson so people at home can see. So P naught was 550. Let's see, let's say times n is 2 to the power of t, little t, divided by capital T was 3. I think that's it. That's the model. Exponential function. It's based on t. I'm going to go with it. Okay. Find an equivalent model of this form. So now we want to find, we want to equate this to an exponential model. Do we have a rate? We have, let me think about it. Well, the initial amount is 550, so we need the rate. So we want to convert that. Only thing we don't know is the rate, so we need to solve for the rate. Okay, I think we can do this. So I'm trying to do it without looking at support, right? So let's do this. I'm going to take some notes. So we have what we just found. Okay, I'm going to go back to the to Pearson. Let me see. Do I have that up top? Okay. I mean, so if I go back to the tablet, right? So let me kind of write out what's going on. So basically, we want to find an equivalent. We want to take this P naught times n to the power of little t over big T, and we want to match it up to, we're going to have P naught e to the kt, right? So we want to find an equivalent exponential of the form on the right, right? So let's fill in what we have on the left. P naught is 550. Little n was 2. Little t is part of the function, so we're going to let that be. And big T was 3, right? We're going to set that equal to, again, the initial amount is 550, and I'm just kind of going off the cuff, times e to the power of k we don't know, and then we're going to say times t. Let's see if we can solve for k. Let's see, is there anything else that we can do? Okay, let's solve for k. So first thing we can do, we can divide both sides by 550, so they're going to cancel each other, right? Now, if we want to get those things out of the exponent, we would take the natural log on both sides, right? So we would say the natural log of this thing, and we would say the natural log of this thing. On the right, natural log and e are going to cancel each other out. On the left, if we use log rules, this is going to become the same as t over 3 times the natural log of 2 equals k times t. I'm hoping that the t's cancel, and they look like they will cancel, right? So now if we divide both sides by t, if we say divided by t and divided by t, you got a t on top, t on bottom. This t is going to cancel that one. This one, we're golden now. You know, we're right as rain. We're good to go. So now we have an expression for k. K, our rate is going to be 1/3. Let's write that 3 a little bit better. 1/3 times the natural log of 2. Now we have an expression for k. So if we want to put it in the analogous exponential form, our p of t is going to be equal to basically the 550 times e to the whatever that number is. We need to crunch that number. I'm just going to say k times t, right? But we got to use the above k. Okay. So now I'm just going to hop back over to Pearson. I'm going to have to crunch that number, and I think we're ready to answer the question. That was actually fun. I never done that. Okay, so the initial amount was 550, and we just need to solve for k, right? So I'm going to go crunch the number. Let me open up my trusty dusty rusty. Nope, not that one. Come on. Come on. I'm tripping. It keeps jumping around. Hang on. All right, I was trying to move too fast, and it wasn't like my touch wasn't registering. It's going to be this one. Okay. Reload and refresh. Come on. Okay, that looks good. So I'm just going to solve for k. I'm going to crunch that number. I'm going to say 1/3 times the natural log of 2. Oh, natural log of 2. Okay. And I get round to 4 decimal places as needed. 2310. Okay, let's go 2310. 0.2310. We're going to cross our fingers. Awesome sauce, right? We're going till 7:15, so we're doing pretty good on time. Okay, there should be questions there. I know it is what it is. Just do the best you can. You know, if you have questions, you can ask me. I know that my energy can be a little bit like this. So, but you have support. You totally have support. You're not in this alone. Although we're always alone, you know, we always have support. We're never really alone. You know what I mean? You just have to speak up and ask for help. And you have a lot of people that just want to help. Aside from me, at least the tutors, Pearson is nothing but help. Let's go forward and try another question. That was fun. Find an exponential function of this form. This is kind of a repeat. I'm going to kind of skip this one just because it looks too similar. Take the derivative. Yes, let's do this. All right. Let me take some notes. So I think in the past we talked about the derivative of e to the x. Now we want to see the derivative of some other base to the power of x, right? So this is question number 8. Question number 8. This comes from section 2.6, question 13. We're asked to differentiate. Hopefully you've already watched my lectures for this. Y equals 18 to the power of x, okay? Let's hop over to the tablet. So one of the new concepts that we introduced here, let me just go ahead and move this down to the next page. So one of the concepts that we talked about here is how to differentiate this. Now, differentiating this is actually the same as what we were doing before with one minor twist, right? So then dy by dx, the derivative of e was itself. So this derivative here is also going to be itself. If we had an exponent, we would say times the derivative of the exponent, but the derivative of x here is 1, so we can ignore that for right now. And then we're also going to say times, in this case, it's going to be the natural log of 18. So this natural log component, we actually were doing it last time, but because we were doing base e, we weren't aware of it. Because natural log of e is 1, so we weren't really aware of it. But that's the added component, right? You got to say times the natural log of whatever that base is. So that's it, really. Nothing else to do there. Natural log of 18 times 18 to the power of x. That's what the derivative is going to be. Okay. Let's hop over to Pearson. And it's just going to be, let's do double parentheses, ln of 18 times 18 to the power of x. So this is very similar to the derivative of e to the x. Remember, the derivative of e is itself, but now the added part is times the natural log of the base. Okay. So, because again, remember, ln of e is 1, but now we have some base other than e. So this one is going to be the natural log of 16. This derivative is going to be ln 16 times 16 to the power of t. And I got something that gives me an error, but we're good to go. Okay. So we would say 7 times the natural log of 11 times 11 to the power of x. Hopefully I wrote it okay. Okay. Let me check the chat. Chat looks okay. On to the next one. Take the derivative, right? Okay, so the first part, we're going to have the natural log of 3, so ln of 3. Then the exponent stays, you keep itself, so 3 to the power of x to the 6 plus 2. And then we got to say times the derivative of the exponent. So we're going to say times, I was at 6x to the power of 5, and I think that's it. Okay. If there are questions, just let me know. We can talk about it. So that was like the chain rule with this new base and the derivative of exponentials, right? So there's about 3 different concepts in there. Maybe some more. There are more concepts there as well. Okay, so this one's going to be 590 times the natural log. So I'm going to say ln of this. I'm going to do, we don't need parentheses. 1.765 times the exponential itself, so the 1.765 to the power of t. And I think the exponent we can ignore because it's nothing. It's the derivative of t is just 1. Let me think about it. Let me see if they accept this. Okay. Okay. Let's go on to the next one. So here we need to do product rule. I'm actually going to write this one out because this one has a has a good amount of stuff going on. Okay, this is question number 13. This comes from section 2.635. I'm sorry, this is a random thing. Even though it's dark now, but this is my favorite time of year. The days are getting longer. Is it like a full moon? I need to do a time lapse of the moon because it just moves so fast. I wish I had thought about that. I'll do that later. But I'll be doing like time-lapse videos out my window, man. The one from the other day was, it don't even look like Earth. I'm like, is this real? I was like, yeah, it's crazy. But it's just beautiful. But I was bringing that up because, you know, my other class, the sun is actually still up when we get out of class now because the days are getting longer. So it makes me excited. Okay, we're asked to differentiate. I know, it's just a random tangent. Let me see my time. We're good. Oh, we're almost out. Oh, no. We want to differentiate. But we got a good amount done today. Okay, we have this g of x equals x to the power of 4 times 8.2 to the power of x. All right, let's hop over to the tablet. Boom, just like that. Okay, so if we want to find g prime, we need to use the product rule. So g prime, that's going to be the first, which is this guy, times the derivative of the second. So we're going to say d by dx of this thing, 8.2 to the power of x, okay? So the first times the derivative of the second plus the second times the derivative of the first. Okay, that's it. So then we go back and find those derivatives. So then we're going to have this x to the power of 4. That one's going to be the natural log of 8.2 times 8.2 to the power of x, okay? I think that's all there. Then we're going to say plus the 8.2 to the power of x persist, and the derivative there is going to be 4x to the power of 3. Now we could factor, let me highlight what's common to both of these terms. They both have this 8.2 to the power of x, 8.2 to the power of x, and there's actually another one. Let me do style, I'm going to do blue, and they both have x to the power of 3. I'm going to highlight those in orange. So there's this, I know this is 4, let me do this again, like this, orange. Okay, so we can factor out the blue and the orange from both of these, right? We have to make some adjustments, but let's factor those out. So we can factor out 8.2 to the power of x. I want that to be second. And they both have x to the third. Okay. And what we're going to be left with in the first term is going to be x times the natural log of 8.2. And then the second one we're going to say is plus 4. Okay, I think that's about the best that we can do. So if you guys are still hanging in there, you are a trooper. We are almost done. We got like, let me see. I don't want to keep you for no more than 10 minutes. We'll hang out for like right at about 10 minutes and then we'll call it a night. Okay, I'm going to go with this. I don't see anything else that combines. So let's submit this and see what happens. I'm going to go back to Pearson. All right, so we got, and I'm just going to do my parentheses, x to the power of 3. We got 8.2 to the power of x. And we also have x times the natural log of 8.2 plus 4. Look at God. Look at God. All right. Hopefully I can get some smiles. You know, I'll probably be even more animated and silly if we were in person, but I just do it to try to change up the energy and like just get a smile on your face. But because I know how this stuff feels, like I've been there. The only way, like with this stuff, especially once you master those shortcuts, you just got to take your time. Trying to follow somebody else's work in math will bore a hole in your head. It even does it to me to this day when I try to follow anybody else's work. So what I have to do is do it myself. Take it step by step, line by line, and do it myself. That's the only way you're going to see it. But trying to follow somebody else's work, when I'm doing the presentations, my recommendation is just get ideas on what to do. But this is a really personal thing for each person. That was totally redundant. But it's personal, right? So I don't expect you to follow what I'm doing. I expect you to like get ideas and see that it's possible. And then take it and apply it and bring it to life yourself. But everybody has to get intimate with it. Anybody that's trying to get through this material, you just got to get intimate with it yourself. Let me take some notes here. This is question number 14. This comes from section 2.6, question 39. It asks us to differentiate. Okay. And we have this g of x equals, now the denominator is 5x plus 2. The numerator is 3 to the power of x. All right, let's hop over to the tablet. So hopefully you should be able to see like, okay, what technique we're going to use. If we just use the product rule, then there's a good chance that this one is going to be the quotient rule, right? So the quotient rule is the whole low d high minus high d low over low low, right? So let's do it. So then g prime of x, so the bottom, which is this guy, times the derivative d by dx of the top. That's 3 to the power of x. Okay. Low d high minus high, so that's 3 to the power of x, times d by dx, the derivative of the bottom. Okay. All over the bottom squared, low low. Okay. Low d high minus high d low over low low. Okay, if we evaluate all of those terms or expressions, we got this 5x plus 2. The derivative of 3 to the power x is going to be the natural log of 3 times 3 to the power of x, okay? Minus 3 to the power of x. And the derivative there is just going to be 5. All over, we got this 5x plus 2 squared, okay? They don't both have the 5x plus 2. They do both have the 3 to the power of x. I mean, we could factor that out, but I don't get anything to cancel. We could factor that out. If we factor it, we'll get this. If we factor out that, let me highlight what I'm factoring. So they have this and this, right? Both terms have the thing in blue. They both have the thing in blue, right? So if I factor out that blue thing from top, even though nothing cancels, it gives me 3 to the power of x. Then I'm left with we can do it as the natural log of 3 times this 5x plus 2 minus 5. And we could expand that a little bit further, but nothing really cancels. We just would be expanded just for the sake of being expanded. We got this 5x plus 2 squared. Okay. Okay, so what I'm going to do, I'm going to glance at how, this is the answer that I got. I'm going to box this for right now. Box. Okay. And I'm actually going to look at the viewing example. How to use a pendulum. Oh, it's Turner. Okay. I got to clean. Okay, let me go to Pearson. And I want to see how they submitted their final answer. Oh, they don't have a viewing example. Okay. Well, I'm going to go with what I have. 3, let's see, on top, we have 3 to the power of x, parentheses, natural log of 3 times, we got this 5x plus 2, okay, and then we have this minus 5 right there. And on bottom, we have this thing squared, and the thing being squared is 5x plus 2. Let me see. All right, now only other thing we can do, if it marks it wrong, we can distribute that natural log of 3. But nothing really cancels, so okay, they took it. All right, that would have been like being redundant. The same thing, you know. Let's do one more. We'll let the next, whatever the next one we do, we'll let it be the last thing. Yeah, let's do this. So we've explored taking the derivative with the base other than e. Now we want to look at taking a derivative with the base other than, of a log where the base is not e, right? I think last time we said the derivative of natural log. Remember that natural log is common log base e. Okay, and so the derivative of natural log was 1 over x, or 1 over whatever the inside part was. So this is the same thing, but we got to account for that other base, right? So this is question number 15. This comes from 2-6 question 25. We're asked to differentiate. Actually, I think I might do one more after this just so we can get another version of this. So I'm going to have y equals the log base 12 of x, right? Let's hop over to the tablet. Okay, so the derivative here is just like, so then let me see, our dy by dx is, let me see, if it were a natural log, it would be 1 over x. So it's still 1 over x, but then you got to say times 1 over the natural log of 12. So that's the added part. Okay, and then essentially that's it. Okay, so I'm going to hop back to Pearson and submit that result. I'm going to write it in the following way. 1 over, we got x times the natural log of 12. Okay, let's do another one. Let me box that answer that I just got. Paste. I'm going to put this in a box. That looks good. Let's do this one. Let me see my time. I don't want to keep you past the 10-minute mark. So this is number 16. Let me get a pen, take some notes. This comes from section 2-6. That's not a 6. Come on. 29. We're asked to, let me just copy and paste because I don't feel like writing that. Differentiate. Let me copy and paste. And let me actually go ahead and get a copy of this. Okay. And then we have g of x. We got the log base 29. We got 6x minus 4. Okay, let's hop over to the tablet. This will be the last one. Okay. All right, so just like for natural log, it's the derivative of natural log was 1 over that inside stuff times the derivative of the inside stuff, but we got to add on that natural log part, right? So all the changes are going to be g prime is going to be 1 over the natural log of 29. That's the new part. Then it's just going to be 1 over 6x minus 4. That's an old part. And then we got to say times the derivative of 6x minus 4. So that's going to be 6. Let me see. So then, I mean, that's essentially it. I'm going to submit that. I'm going to like put it all into one thing. Let me hop back to Pearson. And I'm going to write it as on top, I think we just have 6. On bottom, we have the natural log of 29 times, in parentheses, 6x minus 4. Hopefully I'm not missing something. Okay. I kind of want to do another one, but I'm going to let you go. So I think that's enough. I'm having too much fun, but I know how you might feel, so it's like it's okay. That's enough for right now. Okay, so just practice, ask for help. You know, you're not alone, and it's totally okay. You know, just do the best you can. Link up with your tutors, link up with your classmates, make use of the Ask My Instructor. Email me. If I don't respond to an email, just ask me during class time. We could take class time to talk about stuff. I know my explanations might seem a little intense, but that's why I encourage you to kind of consult other people so you see it's not just me. And a lot of times, especially the tutors and the students, your classmates, especially when they get it, they have a way of saying it where it's much more simple. Like they'll be like, don't worry about that. All you got to do when you see this is this. Like people use that all the time. I used to do it. I'm not aware of those little tricks anymore, and I look for them, but I try to say what I think you need to hear. And then your peers can help you filter some of that stuff. But you just got to push. You got to push. Okay, don't be intimidated. You have a lot of support. Okay. All right. Let's go paper. I'm gonna just kind of show this. Let me actually before I can I do it here before we? Okay, I'm gonna have to disconnect it. So with that being said, let me go here. Let me go here. That is showing. Let me, because I want to go ahead and share these notes before I get off, because once I leave, I'm going to forget. I want to send it to Box, the PDF. All the pages are fine. Right into you guys thing. Let me do the margins. I'm going to send a Box, okay? So now I actually am sending a PDF to our folder, so you can get a copy of all that stuff you saw me writing. You should be able to see it. And I am actually going to hop here. Let me check the chat real quick. Okay, the chat looks good. So again, I'm available for support. You have support. Please take advantage of it. Between me, the tutors, and your classmates, Pearson, and the internet, just take advantage of it and do what you got to do. Okay? But you have support. It's going to be okay. Also, I just want to say, be aware that we get unlimited attempts at all assignments. It's set to take your highest score. You can even submit all assignments late. That's like homework, quizzes, and exams. You can submit them late for only 10% late penalty. Okay? So if there aren't any burning questions, we're actually going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace. Sounds like it's always on. Let's see if I can do some bars. Turn my headphones up. All right, guys, good luck. Okay, I was just trying to hang out with some people.